In this video, we're going to look at basic derivative rules. So the first is a derivative of a constant. Rather than having to compute the derivative with the limit definition with the f of x plus h every time, what we'd like to do is be able to compute the derivative more quickly using patterns and rules that we can follow that work every time. So the first is the derivative of a constant. Here's the graph of y equals a constant, and you'll notice that its slope is 0. And so therefore, the slope of every tangent line anywhere is also 0. Okay, so the derivative of any constant, where c is a constant, is 0. So if f of x is 2, for example, you have the function just plain 2, then f prime of x is 0. Or the derivative of 3 is 0. Simple. The power rule is a fun rule. It gives us a way to differentiate x to any power, and it works with any power, whether the power is positive, negative, a fraction, a decimal, whatever. It always works. So the power rule says that the derivative of x to the power of n is equal to n times x to the power of n minus 1. Now, explaining why this rule works or showing it or proving it is actually pretty difficult to do, so we're going to skip that right now. But we'll do some examples and you'll see that it does in fact work. So for example, if y equals x squared, then its derivative, according to this rule, is, well, we take this exponent n and we bring it down out front. So this exponent 2 comes down out front, and then we have times x to the power of the original power minus 1. So x to the power of 2 minus 1 is just 1. So there's an exponent of 1, which is just 2x. Or if f of x equals x to the 6th, okay, we bring that 6 down out front, and then we have times x to the power of 5, decrease the power by 1. Or a fun one, if y equals x to the 1st, well, you bring that implied exponent of 1 down out front, and then you have times x to the 0. But anything to the 0 power is 1. So the derivative of y equals x is actually just the number 1. It's the coefficient of x. Okay, the derivative of plain x is 1. Now for the derivative of a constant times a function, so if you have the derivative of some constant c times a function f of x, you can bring that constant out, and it goes back to the limit rule. There is a property that says you can bring a constant out to the front of a limit. And because technically a derivative is a limit, we can bring that constant out to the front. So it's the same as c times the derivative of f of x. Now let's look at an example here. If f of x equals 4 over x to the 5th, let's find its derivative. Well, we don't have a derivative rule for a fraction yet. So instead, we're going to have to rewrite this so that we can use the rules we do have. And the one we want to really use here is the power rule. Okay, so we need to rewrite this somehow before we differentiate it as x to a power. So what we can do is rewrite that denominator, though, as x to the minus 5. So the function f of x we can write as 4 times x to the negative 5. Then its derivative, okay, for the derivative of this, the 4 just comes out front because it's a constant. So it's 4 times the derivative of x to the minus 5. For that we use the power rule, so we bring the minus 5 down out front. And we have x to the negative 5 minus 1 is negative 6. So this derivative simplifies to negative 20 times x to the negative 6, or you could write it as negative 20 over x to the positive 6. Either of those versions is a good solution, a good way to write that derivative. Let's do another example. Find the equation of the tangent lines, equations of the lines, to the graph of f of x equals 4 over x at 2 and at negative 1. Then we're going to sketch a graph of f and the tangent lines. And then we'll look at what is the one value of x at which the derivative is not defined, which has to do with non-differentiability. First, let's find the derivative. So again, we have a fraction, so we're going to need to rewrite it first so that it is not a fraction. So let's bring this x up to the numerator and write this as 4x to the minus 1. Then its derivative by the power rule. We bring the negative down out front, so we'll have 4 times negative 1, or negative 4. X to the negative 1 minus 1 is negative 2. That's the derivative. Now let's write it with a positive exponent to make it easier to compute the numbers with. So we're going to put that x to the minus 2 in the denominator and write it as x squared. So negative 4 over x squared. So that's a function that tells me the derivative, or the slope of the tangent line, at any point. So if I now want to find f prime of 2, I will plug 2 into this formula here, negative 4 over 2 squared. That's negative 4 over 4, or negative 1. So that tells me the slope of the tangent line at x equals 2 is negative 1. And let's go ahead and compute the other derivative as well. F prime of negative 1 would be negative 4 over, parentheses here, negative 1 all squared. Negative 1 times itself is positive 1, so we get negative 4. Okay, now let's find the equations of the tangent lines and sketch the graph. So to find an equation of a tangent line, you need to have a point and a slope. These two values right here are my slopes, but I also need a point. So if I want to find the equation of the tangent line at x equals 2, I need to find a point on that line. And the only point we can use is the point at x equals 2, because we don't know any other points on the line. So I'm going to find f of 2 to find the coordinating y value. So f of 2 is equal to 4 over 2, or 2. So 2 comma 2 is a point on the function f of x, and negative 1 is the corresponding slope at that point. And let's go ahead and find f of negative 1 as well. So f of negative 1 is 4 over negative 1, or negative 4. Happens to be the same as the slope. Okay, now that we have all of our information, let's put it together as an equation of a line. So let's do this one first. We have that 2 comma 2 is a point on the function, and the slope is negative 1 at that point. So using point slope form, that's this, let's put this in black, that's the general form, y minus y1 equals slope times x minus x1. If I plug in this point for my x1, y1, and this for my slope, then I have y minus y1 is 2 equals the slope, negative 1, times x minus x1 is 2. Now that's an equation of the line. We can stop there, or you can solve for y and put it in slope-intercept form, which many students prefer. So I'm going to go ahead and do that. So if we solve this for y, we'll distribute that negative to get negative x. This will become positive 2, and then plus another 2 will give me plus 4. Over here, putting this information into an equation of a line, we have that the point negative 1 comma negative 4 is on the line, and at that point the slope of the line is negative 4. So using the point slope form again, we have y minus y1 is right here, negative 4, equals the slope, negative 4 times x minus x1, negative 1. Simplifying this, we have y plus 4 equals, distributing that negative here, we have negative 4. This becomes positive 1, but times negative 4 is also negative 4. And then if we subtract 4 from both, oops, I left off an x. If we subtract 4 from both sides, we get y equals negative 4x minus 8. Now let's sketch the graph of 4 over x and the tangent line. So 4 over x is the graph that I'm sketching. We'll just plug a few points here. Okay, notice I cannot plug in 0. This is a rational function with a vertical asymptote at 0. So let's sketch that asymptote in there. Okay, let's plug in 1. When x is 1, y is going to be negative 4. Down here. When x is, let's see what, it should be an asymptote there. If I plug in a half, let's get a little closer to that x-axis. we would have 4 divided by half. That's the same as 4 times 2. Oops, is that supposed to be negative? No, positive. I don't know why I put negative there. Hold on, let's back up here. Positive 4, you're probably confused there. Okay, if we plug in a half, 4 divided by a half is 8, so it is going to hug this line right here, that asymptote. Let's plug in a larger value of x, though. How about 2? 4 divided by 2 is 2, so 2 comma 2. If I plug in, I want to do easy values here, so I'm going to pick 4, because 4 divided by 4 is 1. 1, 2, 3, 4, 1. And then if you plug in something like 8, 4 divided by 8 is a half, it's going to hug this horizontal asymptote. This is a rational function that also has a horizontal asymptote at the y-axis, or y equals 0. So if we sketch the function, it's going to look something like this. And 4 over x, let's see, if we plug in negative values, the numeric values are the same, they're just all negative. So negative 1, negative 4, negative a half, negative 8, negative 2, negative 2, negative 4, negative 1, and it will have the opposite shape there. Doesn't have to be perfect, we just want it to be kind of accurate enough to really see these lines. So we were looking for the slope at 2. Let's do this one first. So the slope at 2 we discovered is negative 1, and then it goes to the point 2 comma 2. So that means right here at 2, 2, there's that point. The slope of the tangent line is exactly negative 1. So up 1 over 1, up 1 over 1. There's the tangent line, and the equation of this line is given by y equals negative x plus 4. So if I draw it exactly correct, it would have a y-intercept of 4 there, which it looks like it does, positive 4. And this one, the other tangent line, let's see, touches at x equals negative 1, has a slope of negative 4, and it goes through the point negative 1 comma negative 4. So here's negative 1, negative 4, and because the derivative at negative 1 is negative 4, let's count it out here. I can go up 1 over 1, 2, 3, 4, a little bit off the graph there, or down 1 over 1, 2, 3, 4. So it should have a y-intercept of, oh, maybe I made an error there, because I'm getting negative 1, I'm graphing it in the wrong place. Negative 1, negative 4, there we go. 1, 2, 3, 4, yeah, that crosses at negative 8 there. 1, 2, 3, 4, up and over. So there's this tangent line, which also has a negative slope. Okay, let's look at some more rules. Let's find the derivative of y equals cx, where c is a constant. Well, because the derivative of y equals x is 1, and we can pull a constant out front, the derivative of a line of the form y equals cx can be found by pulling the c out front and then multiplying times the derivative of x, which is 1, so we just get c. What I'm saying here is that the derivative, or the slope of a tangent line to a line, is actually the slope of the line itself. So the derivative of y equals cx is just the constant, or the slope c. So if the function is y equals 4x, then its derivative is simply y prime equals 4. It's the slope of the line 4x, which is the coefficient of x. Or if, for example, f of x equals negative 11x, then its derivative is negative 11. And last, we have the derivative of a sum or a difference. So if you have the derivative of two functions being added or subtracted, f of x plus or minus g of x, because you can split a limit of a sum into a sum of two limits, and a derivative is really a limit in the background, that's what's going on, this can be, a derivative of a sum or difference can be split into a sum or difference of two derivatives. So it can be written as the derivative of f of x plus or minus the derivative of g of x. So in this last example here, we're going to find dy dx. That's the derivative with respect to x for this polynomial. So dy dx, over here, dy dx equals to, okay, the derivative of the first term minus the derivative of this term plus the derivative of this term minus the derivative of 2, according to this rule. So for the derivative of 3x to the 4th, we bring the 4 down and we multiply it times that 3 to get 12 times x to the power of 4 minus 1 is 3, minus the derivative of the next term. We bring the 2 down and multiply it times the negative 5 to get negative 10 times x to the power of 2 minus 1 is 1. Plus the derivative of 10x, that's an example of this, it's just plain 10. And the derivative of a constant by itself is actually 0. So just cleaning it up a little bit here, then dy dx can be written as 12x cubed minus 10x plus 10.